The evolution of cosmic understanding, from ancient myths to the Big Bang. For as long as humanity has gazed up at the night sky, we've been captivated by the splendor and mystery of the cosmos. Countless stars shimmering like diamonds have inspired wonder, curiosity, and a profound desire to understand our place in the universe. Today we embark on an extraordinary journey through time and space to explore one of the most profound questions ever asked. How did the universe begin? The Big Bang Theory stands as the prevailing cosmological model that describes the origin and evolution of the universe. It proposes that approximately 13.8 billion years ago, the universe expanded from an unimaginably hot and dense state into the vast cosmic expanse we observe today. But how did we arrive at this groundbreaking understanding? The journey to the Big Bang Theory is a tapestry woven from centuries of observation, mathematical ingenuity, and relentless questioning. In this comprehensive exploration, we'll delve deep into the history of cosmology, from ancient civilizations that mapped the stars to modern scientists who unraveled the mysteries of space-time. We'll examine the pivotal discoveries, the brilliant minds, and the revolutionary ideas that have shaped our understanding of the universe. Join us as we trace the evolution of cosmic thought, from the early myths and geocentric models to the heliocentric revolution and beyond. Our quest begins with the earliest civilizations, whose lives were intimately connected to the heavens. The movements of celestial bodies guided agricultural cycles, navigation, and spiritual practices. In ancient Egypt, the sky was personified by the goddess Nut, arching over the earth and birthing the sun each day. The Egyptians built monuments like the pyramids aligned with stellar constellations, reflecting their cosmic beliefs. Similarly, the Babylonians meticulously recorded celestial events, developing one of the earliest known star catalogs. They interpreted astronomical phenomena as omens, believing the gods communicated through the stars. In ancient China, astronomers like Shi Shen and Gande documented comets, eclipses, and novae, contributing to a rich astronomical tradition. Their records, dating back to the 4th century BCE, are invaluable to modern astronomy for understanding historical celestial events. The ancient Greeks took a pivotal step by seeking natural explanations for the cosmos. Philosophers like Thales of Miletus proposed that the world could be understood through reason and observation. One of the most influential was Aristotle, 384–322 BCE. In his treatise On the Heavens, Aristotle posited a geocentric universe, a cosmos with Earth at its immovable center. He described the heavens as composed of 55 concentric crystalline spheres, each carrying celestial objects in uniform circular motion. Aristotle introduced the concept of the ether, an unchanging, perfect substance filling the celestial realms. The Earth, by contrast, was imperfect and subject to change. This dualistic view of the cosmos reflected and reinforced philosophical and religious beliefs about perfection and order. The geocentric model was further refined by Claudius Ptolemy, 100–170 CE, whose work Almagest became the definitive astronomical guide for over 1,000 years. Ptolemy introduced complex mechanisms like epicycles, deferents, and aquants to account for planetary motions and retrograde movement. Despite its complexity, Ptolemy's model was remarkably successful at predicting celestial events. It aligned with the philosophical notion of uniform circular motion and satisfied observational data available at the time. During the Islamic Golden Age, 8th–14th centuries, scholars like al-Battani, Ibn al-Haytham, and Nasir al-Din al-Tusi preserved and expanded upon Greek astronomical knowledge. They critically examined Ptolemaic astronomy, improving astronomical tables and instruments. Al-Tusi, for instance, developed the Tusi couple, a mathematical device that generated linear motion from circular motions, refining models of planetary movement. These scholars' meticulous observations and critiques sowed seeds of doubt about the geocentric model's accuracy, setting the stage for a paradigm shift. The Renaissance ignited a transformation in Europe. The invention of the printing press by Johannes Gutenberg around 1440 revolutionized the dissemination of knowledge. Amid this intellectual fervor, Nicolaus Copernicus, 1473–1543, a Polish mathematician and astronomer, challenged the long-held geocentric model. In his groundbreaking work De Revolutionibus Orbium Coelestium, published in 1543, Copernicus proposed a heliocentric model with the sun at the center. Copernicus's model suggested that Earth rotates on its axis daily and orbits the Sun annually. This explained the retrograde motion of planets as an optical effect due to Earth's movement, eliminating the need for complex epicycles. While revolutionary, Copernicus's ideas were met with skepticism. The notion that Earth was not the center of the universe was unsettling and contradicted theological doctrines. His work remained relatively obscure until further evidence could substantiate it. Enter Tycho Brahe, a Danish nobleman and astronomer renowned for his precise and systematic observations. Tycho meticulously charted the positions of stars and planets for over 2 decades, amassing data of unprecedented accuracy. He observed a supernova in 1572 and a comet in 1577, phenomena that contradicted the notion of unchanging heavens as they occurred beyond the moon's orbit. Tycho proposed a compromise, the Tychonic system, where Earth remained stationary at the center. The moon and sun orbited Earth, but other planets orbited the sun. This model preserved geocentric principles while incorporating Copernican calculations. After Tycho's death, his assistant Johannes Kepler inherited the valuable data. A brilliant mathematician and astronomer, Kepler sought to uncover the divine harmony he believed governed the cosmos. Through rigorous analysis, Kepler formulated his 3 laws of planetary motion. First law, 1609. Planets move in elliptical orbits with the sun at one focus. Second law, 1609. A line joining a planet and the sun sweeps out equal areas during equal intervals of time. Third law, 1619. The square of a planet's orbital period is proportional to the cube of the semi-major axis of its orbit. Kepler's laws provided a robust mathematical foundation for the heliocentric model, greatly improving its predictive accuracy and moving astronomy toward a physics-based science. Around the same time, Galileo Galilei advanced observational astronomy using the telescope, an instrument he improved upon significantly. In 1610, Galileo published Sidereus Nuncius, the Starry Messenger, detailing his discoveries, mountains and craters on the moon, indicating it was not a perfect celestial sphere. 4 largest moons of Jupiter, now known as the Galilean moons, proving not all celestial bodies orbit Earth. Phases of Venus, supporting the heliocentric model. Countless stars, revealing that the universe was far more extensive than previously thought. Galileo's work provided compelling evidence for the heliocentric model and challenged the established Aristotelian cosmology. However, his advocacy brought him into conflict with the Catholic Church. In 1633, Galileo was tried by the Inquisition, found vehemently suspect of heresy, forced to recant his support for heliocentrism, and sentenced to house arrest for life. Despite this, his work spread across Europe, igniting scientific discourse and inspiring future generations. Building upon the foundations laid by his predecessors, Sir Isaac Newton synthesized the laws of motion and universal gravitation, uniting celestial and terrestrial mechanics. Newton's law of universal gravitation stated that every mass attracts every other mass through a force acting along the line, intersecting both points. His 3 laws of motion described the relationship between an object and the forces acting upon it, forming the cornerstone of classical mechanics. Newton's work explained why planets orbit the sun and moons orbit planets. His laws enabled precise predictions of planetary motions, comets' paths, and tides, further validating the heliocentric model. The shift from a geocentric to a heliocentric universe was more than a change in astronomical models. It was a profound transformation in human thought. It signaled the emergence of the scientific method, a reliance on observation, experimentation, and mathematics to understand the natural world. These pioneers challenged entrenched beliefs, often at great personal risk, driven by an insatiable curiosity and a commitment to uncovering the truth. Their collective efforts set the stage for the revolutionary discoveries of the 20th century, where the nature of space, time, and the universe itself would be redefined. As the 20th century dawned, physics stood at a crossroads. Classical mechanics, formulated by Newton, had been unchallenged for over 2 centuries, yet anomalies in electromagnetic theory and the behavior of light signaled the need for new ideas. Enter Albert Einstein, 1879-1955, a patent clerk in Bern, Switzerland, whose radical thinking would revolutionize our understanding of space and time. In 1905, Einstein published 4 groundbreaking papers: photoelectric effect, introducing the concept of light quanta, photons, laying the groundwork for quantum mechanics. Brownian motion, providing empirical evidence for the existence of atoms. Special theory of relativity, proposing that the laws of physics are the same in all inertial frames and that the speed of light is constant. Mass-energy equivalence, formulated in the famous equation E=mc². These works disrupted classical notions and set the stage for further breakthroughs. However, it was Einstein's general theory of relativity, published in 1915, that would profoundly alter our conception of the universe. General relativity extended the principles of special relativity to non-inertial frames and introduced a new understanding of gravity. Einstein proposed that gravity is not a force acting at a distance, as Newton described, but rather the result of the curvature of spacetime caused by mass and energy. Objects move along the straightest possible paths, or geodesics, in this curved spacetime. In Einstein's own words, matter tells spacetime how to curve, and spacetime tells matter how to move. The core of general relativity lies in the Einstein field equations, which relate the geometry of spacetime, expressed by the Einstein tensor g mu nu, to the energy and momentum within that spacetime, represented by the stress-energy tensor t mu nu. These equations are highly complex, consisting of 10 interrelated differential equations. Solving them requires sophisticated mathematical techniques, but they have led to remarkable predictions. One of the first confirmations of general relativity came in 1919 during a total solar eclipse. Sir Arthur Eddington led an expedition to observe starlight passing near the sun. According to general relativity, the sun's mass would curve spacetime and bend the path of the starlight. The observed deflection matched Einstein's predictions. The successful confirmation catapulted Einstein to international fame and solidified general relativity as a cornerstone of modern physics. Einstein realized that his equations permitted dynamic solutions, universes that could expand or contract. This conflicted with the prevailing belief in a static universe. Einstein later regarded the cosmological constant as his biggest blunder, after observations showed the universe was not static. Ironically, the cosmological constant has resurfaced in modern cosmology to explain dark energy and the accelerated expansion of the universe. The evolution of cosmology, from expanding universe to the Big Bang theory. While Einstein grappled with the implications of his equations, observational astronomers were making discoveries that would revolutionize cosmology. Central to this was Edwin Hubble, 1889-1953, an American astronomer whose work extended our understanding of the universe's vastness. In the early 20th century, astronomers debated whether the Milky Way constituted the entire universe, or if spiral nebulae, observed through telescopes, were distant island universes. In 1924, Hubble settled the debate by identifying Cepheid variable stars in the Andromeda Nebula, using Henrietta Swan-Leavitt's period luminosity relationship. By calculating the distance to Andromeda, Hubble demonstrated it was a separate galaxy beyond the Milky Way. Cepheid variables are stars whose brightness fluctuates in a regular pattern. Leavitt discovered that the period of these fluctuations correlates with their intrinsic luminosity. By measuring the period, astronomers can determine a Cepheid's true brightness, and by comparing it to its apparent brightness, calculate its distance. Building on this, Hubble, along with Milton Humason, measured the distances to numerous galaxies and analyzed their spectral lines. They observed a redshift in the light from distant galaxies. The wavelengths were stretched toward the red end of the spectrum. This redshift indicated that galaxies were moving away from us. Hubble plotted the recessional velocities of galaxies against their distances and discovered a linear relationship, now known as Hubble's law. Hubble's law can be expressed as V equals h0 times d, where v is the recessional velocity of a galaxy, h0 is the Hubble constant, and d is the distance to the galaxy. This implies that the universe is expanding uniformly. Galaxies are moving away from each other, and the farther a galaxy is, the faster it recedes. To visualize this, imagine galaxies as dots on the surface of a balloon. As the balloon inflates, the distance between all points increases. Importantly, there's no central point of expansion. Space itself is expanding. As Hubble noted, the outstanding feature is the possibility that the velocity-distance relation may represent the de Sitter effect, and hence that numerical data may have a bearing on the curvature of space and the general theory of relativity. Prior to Hubble's observations, theoretical groundwork had been laid by Alexander Friedmann, 1888-1925, a Russian mathematician and meteorologist, and Georges Lemaitre, 1894-1966, a Belgian priest and astronomer. In 1922, Friedmann solved Einstein's field equations without the cosmological constant, showing that the universe could be dynamic, expanding or contracting. His Friedmann equations described various cosmological models based on the curvature of space. Independently, in 1927, Georges Lemaitre applied general relativity to cosmology, suggesting that the universe is expanding and proposing what would later be known as the Big Bang theory. Hubble's empirical evidence provided the observational confirmation for the theoretical models of Friedmann and Lemaitre, merging theory and observation into a coherent picture of an expanding universe. Einstein initially resisted the idea of an expanding universe, favoring a static model. However, after visiting Hubble and examining the data, he reportedly conceded, calling his introduction of the cosmological constant his greatest blunder. Georges Lemaitre, both a Jesuit priest and a physicist, was a pivotal figure in cosmology. In 1927, he published a paper titled A Homogeneous Universe of Constant Mass and Increasing Radius Accounting for the Radial Velocity of Extragalactic Nebulae. In it, Lemaitre derived solutions to Einstein's field equations that described an expanding universe. He proposed that the observed redshifts of galaxies were due to this expansion, linking theory with Hubble's observations. In 1931, Lemaitre took his ideas further, suggesting that the universe originated from a single, incredibly dense point he called the primeval atom, or cosmic egg. He envisioned this as a bursting moment where space and time began, leading to the expansion we observe today. Lemaitre's hypothesis was radical, implying that the universe had a beginning, a finite age. This concept challenged the prevailing notion of an eternal, unchanging universe and had profound philosophical and theological implications. Lemaitre wrote, "The evolution of the world can be compared to a display of fireworks that has just ended. Standing on a well-cooled cinder, we see the fading of the suns and try to recall the vanished brilliance of the origin of the worlds." Lemaitre's work combined rigorous mathematics with innovative cosmological models. He bridged the gap between Einstein's general relativity and astronomical observations, laying the foundation for the Big Bang theory. Despite the growing evidence, not all scientists embraced the idea of a universe with a beginning. In 1948, astronomers Fred Hoyle, Thomas Gold, and Hermann Bondi proposed the steady-state theory. They suggested that the universe is eternal and unchanging on a large scale, even as it expands. To reconcile expansion with a constant density, they postulated continuous creation of matter, hydrogen atoms spontaneously forming to fill the voids left by receding galaxies. The steady-state theory appealed to the aesthetic preference for an unchanging universe and circumvented the need for a cosmic beginning. Hoyle, in particular, was a vocal critic of the Big Bang theory. Ironically, it was Fred Hoyle who coined the term Big Bang during a 1949 BBC radio broadcast, intending it as a derogatory label. The mid-20th century saw intense debate between proponents of the Big Bang and steady-state theories. Both models aimed to explain the observable data, but they made different predictions about the universe's past and future. The Big Bang theory predicted a cosmic microwave background radiation, CMB, permeating the universe as a remnant of the early hot, dense state. A specific abundance of light elements formed during nucleosynthesis in the first few minutes after the Big Bang. The steady-state theory did not predict these phenomena, leading to critical tests of both models. In the late 1940s, George Gamow, along with his students Ralph Alpher and Robert Herman, further developed the Big Bang theory. They predicted the existence of the cosmic microwave background radiation, a relic heat from the early universe, cooled to just a few degrees above absolute zero due to cosmic expansion. They also calculated the expected abundances of light elements like hydrogen, helium, and lithium, matching observed cosmic proportions. These predictions provided testable consequences of the Big Bang theory, setting the stage for future observations that would tip the scales in its favor. The early 20th century was a period of profound transformation in our understanding of the universe. Einstein's general relativity redefined gravity and the fabric of space-time, while observations by Hubble revealed that our universe is dynamic and expanding. In the next sections, we'll delve into the critical discoveries that tipped the balance in favor of the Big Bang theory, most notably the detection of the cosmic microwave background radiation and the abundance of light elements. By the mid-20th century, the debate between the Big Bang and steady-state theories hinged on key predictions that could be tested observationally. One of the most critical predictions of the Big Bang theory was the existence of the cosmic microwave background radiation, CMB, a relic radiation permeating the universe, a faint afterglow from the hot, dense state of the early cosmos. According to the Big Bang model, the early universe was a hot, dense plasma of photons, electrons, and protons. As the universe expanded and cooled, it reached a temperature where electrons and protons combined to form neutral hydrogen atoms, a process called recombination, approximately 380,000 years after the Big Bang. At this point, photons decoupled from matter and began to travel freely through space. Over billions of years, the expansion of the universe stretched these photons to longer wavelengths, cooling them to microwave frequencies. This remnant radiation should be observable today as a uniform background glow across the sky. The existence of the CMB was confirmed serendipitously in 1965 by Arno Penzias and Robert Wilson, radio astronomers at Bell Telephone Laboratories. Upon learning of Penzias and Wilson's findings, Dickey reportedly turned to his team and said, "Well, boys, we've been scooped." The two groups published back-to-back papers in the Astrophysical Journal, with Penzias and Wilson describing their observations and Dickey's team interpreting the significance. Penzias and Wilson wrote, "A residual noise of about 3.5 K temperature has been found. It is isotropic, unpolarized, and free from seasonal variations." The discovery of the CMB provided compelling evidence for the Big Bang theory. The radiation exhibited a perfect blackbody spectrum, a characteristic signature of thermal equilibrium in the early universe. For their groundbreaking discovery, Penzias and Wilson were awarded the 1978 Nobel Prize in Physics. Their work confirmed a fundamental prediction of the Big Bang theory and marked a turning point in cosmology. Another pillar supporting the Big Bang theory is the observed abundance of light elements in the universe. The theory predicts that during the first few minutes after the Big Bang, conditions were suitable for Big Bang nucleosynthesis, BBN, the formation of light nuclei from protons and neutrons. In this brief period, temperatures were extraordinarily high, on the order of 1 billion degrees Kelvin. Protons and neutrons collided to form deuterium, which fused into helium-4 with trace amounts of helium-3, lithium-7, and beryllium. The predicted ratios of these elements are hydrogen-1 approximately 75% by mass, helium-4 approximately 25% by mass, and deuterium, helium-3, and lithium-7 in trace amounts. These predictions align remarkably well with astronomical observations and measurements in ancient gas clouds and stellar atmospheres. As noted by physicist Steven Weinberg, the agreement between the calculated and observed abundances is one of the great successes of the hot Big Bang model. Observations of the oldest stars and distant gas clouds provide data on primordial element abundances, uncontaminated by stellar processes. The consistency between observed and predicted abundances strengthens the case for the Big Bang nucleosynthesis model. The large-scale structure of the universe, the distribution of galaxies, clusters, and superclusters, offers further evidence supporting the Big Bang theory. These structures emerged from initial density fluctuations in the early universe, amplified by gravitational instability over billions of years. Cosmological models incorporating the Big Bang framework, dark matter and dark energy successfully reproduce the observed large-scale structures when starting from tiny anisotropies detected in the cosmic microwave background. Galaxy redshift surveys, such as the Sloan Digital Sky Survey, SDSS, and the 2DF Galaxy Redshift Survey, map the three-dimensional distribution of galaxies across vast volumes. These observations reveal a cosmic web consistent with predictions from Big Bang cosmology. Astrophysicist Margaret Geller remarked, "We are seeing the pattern of the universe on the largest scales we can observe, and it's a pattern that tells us about the conditions in the early universe." The alignment and distribution of these large-scale structures align with the growth of initial quantum fluctuations stretched during cosmic inflation, a critical component of the Big Bang model. Refinements and advances in our understanding of the universe. While the Big Bang theory explained many observations, it left certain puzzles unresolved, such as the horizon problem, the flatness problem, and the monopole problem. In 1981, physicist Alan Guth proposed the inflation theory to address these issues. The horizon problem arises because regions of the universe separated by vast distances have nearly identical temperatures and properties, even though they shouldn't have been in causal contact according to standard Big Bang expansion. The flatness problem concerns the observed near-perfect flatness of the universe's spatial geometry. Without a mechanism to drive it towards flatness, any initial curvature would have increased over time, contrary to observations. Guth's inflation theory posits that a fraction of a second after the Big Bang, the universe underwent an exponential expansion, growing by a factor of at least 10 to the 26th power in less than 10 to the negative 32nd power seconds. This rapid inflation stretched any initial curvature and inhomogeneities, effectively solving the horizon and flatness problems. Guth stated, "The inflationary universe provides a possible mechanism for the uniformity of the universe and the absence of exotic relics such as magnetic monopolies. Moreover, inflation stretched quantum fluctuations to macroscopic scales, seeding the density variations that led to galaxy formation. This provides a mechanism linking quantum physics and cosmological structures." Inflationary theory was further developed into new inflation and chaotic inflation models by physicists like Andre Linde and Paul Steinhardt, addressing initial conditions and potential energy dynamics. In the 1970s, astronomer Vera Rubin and collaborator Kent Ford studied the rotation curves of spiral galaxies and found that stars orbit at roughly constant speeds regardless of their distance from the galactic center. This discrepancy suggested the presence of unseen mass, dark matter, exerting gravitational influence. Dark matter does not emit, absorb, or reflect light, making it detectable only through gravitational effects. Additional evidence for dark matter comes from gravitational lensing, where light from distant objects is bent around massive foreground clusters more than visible matter alone can account for. In the late 1990s, two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, studied distant Type Ia supernovae to measure the universe's expansion rate. They discovered that the expansion is accelerating, implying the existence of a mysterious repulsive force termed dark energy. As Saul Perlmutter noted, the results were astonishing. The universe wasn't slowing down due to gravity as expected, it was speeding up. Dark energy constitutes about 68% of the universe's total energy density and is associated with the cosmological constant lambda in Einstein's field equations. Its nature remains one of the biggest mysteries in cosmology. To probe the early universe further, NASA launched the Cosmic Background Explorer, COBE, satellite. In 1992, COBE detected minute temperature fluctuations, anisotropies, in the CMB at the level of 1 part in 100,000. These anisotropies correspond to the tiny density variations that grew into galaxies and large-scale structures under gravity. The discovery provided strong support for inflationary models predicting such fluctuations. WMAP further refined measurements of the CMB anisotropies, producing detailed maps that allowed precise determination of cosmological parameters, including the universe's age, composition, and geometry. WMAP results confirmed that the universe is flat, composed of approximately 5% normal matter, 27% dark matter, and 68% dark energy, and is about 13.8 billion years old. The Planck satellite provided the most detailed measurements of the CMB to date, further confirming and refining the cosmological parameters and supporting the inflationary Big Bang model. As George F. Smoot remarked upon receiving the Nobel Prize in 2006, the COBE results provided evidence about our universe that is crucial to our understanding of the origin of the universe, the formation of galaxies, and the process of cosmological evolution. The discovery of the cosmic microwave background radiation and the observed abundance of light elements provided compelling evidence for the Big Bang theory, shifting the balance decisively away from the steady-state model. Refinements like the inflation theory addressed lingering questions, offering solutions to fundamental cosmological problems and linking quantum fluctuations to the large-scale structure of the universe. The recognition of dark matter and dark energy has expanded our understanding of the universe's composition, revealing that the ordinary matter we see constitutes only a small fraction of the cosmos. Precision measurements of the cosmic microwave background anisotropies by satellites like COBE, WMAP, and Planck have transformed cosmology into a precision science, allowing us to determine the universe's age, shape, and destiny with remarkable accuracy. Yet, many mysteries remain. What is the true nature of dark energy and dark matter? What happened during the Planck epoch, the universe's earliest moments? As we continue to explore and unravel these enigmas, our journey into the cosmos not only answers age-old questions, but also continually inspires new ones. Join us in the next sections as we delve into the current challenges and open questions in cosmology and the cutting-edge research that pushes the boundaries of our cosmic understanding. As our understanding of the universe's origins has advanced, so too have the questions that challenge the limits of physics. At the heart of the Big Bang theory lies the concept of a singularity, a point where density and temperature become infinite, and the laws of physics as we know them cease to apply. General relativity, Einstein's masterwork, describes gravity as the curvature of space-time caused by mass and energy. However, when applied to the extreme conditions of the singularity, general relativity predicts infinities, signaling a breakdown of the theory. To unravel the mysteries of the singularity in the earliest moments of the universe, known as the Planck epoch, the first 10 to the negative 43rd power seconds, we need a theory that unifies general relativity with quantum mechanics, a quantum theory of gravity. Quantum mechanics governs the realm of the very small, particles and their interactions, while general relativity governs the large-scale structure of space-time. Their reconciliation is one of the most profound challenges in theoretical physics. Several approaches aim to develop a quantum theory of gravity. One prominent candidate is string theory, which posits that fundamental particles are not point-like objects but rather one-dimensional strings vibrating at specific frequencies. String theory naturally incorporates gravity and requires additional spatial dimensions, up to 11 in M theory, providing a framework that could unify all fundamental forces. Another approach is loop quantum gravity, LQG, which attempts to quantize spacetime itself, suggesting that space is composed of discrete units or quanta. LQG predicts that spacetime has a granular structure at the Planck scale. As physicist Carlo Rovelli explains, loop quantum gravity indicates that near the Big Bang, the gravitational field has quantum properties that could avoid the singularity. These theories suggest possibilities such as the Big Bounce, where the Big Bang is not the beginning but a transition from a previous collapsing universe. However, without experimental evidence, these remain speculative models. Efforts to test these theories include searching for gravitational waves from the early universe, detecting deviations in cosmic microwave background patterns, and investigating black hole behavior. Yet the extreme energies required to probe quantum gravity are beyond current technological capabilities. Bridging the gap between general relativity and quantum mechanics remains one of the foremost quests in physics. Unlocking this mystery could provide profound insights into the true nature of space, time, and the origins of our universe. The quest to understand the universe's origins has led some scientists to contemplate the possibility of a multiverse, an ensemble of universes existing beyond our observable cosmos. This idea emerges from various theoretical frameworks, including inflationary cosmology and string theory. In eternal inflation models proposed by physicist André Linde, inflation is an ongoing process in different regions of space. While our universe underwent inflation and then slowed to form stars and galaxies, other regions continue inflating, leading to a multiverse of bubble universes. Linde describes it as, the universe is like a fractal, consisting of many inflating regions with different properties. String theory introduces the concept of a landscape of possible solutions, with around 10 to the 500th power different vacuum states, each representing a possible universe with its own physical constants and laws. This immense number of possibilities raises the anthropic principle, which argues that the fundamental parameters of the universe are as they are because they allow for the existence of observers like us. The weak anthropic principle states that our observations are constrained by the requirement of our existence, while the strong anthropic principle suggests that the universe must have properties that inevitably lead to the development of life. Multiverse theories attempt to explain why our universe appears fine-tuned for life. If countless universes exist with varying properties, it is not surprising that at least one would have the conditions necessary for life. However, the multiverse concept is controversial. Critics argue that because other universes are, by definition, unobservable, the theory is not testable and thus falls outside the realm of empirical science. Cosmologist George F.R. Ellis contends, the multiverse may be a metaphysical idea rather than a testable scientific hypothesis. Some propose that evidence for the multiverse might be found indirectly, such as detecting anomalies in the cosmic microwave background that could indicate collisions with other universes. The multiverse theory challenges our understanding of reality and raises profound philosophical questions about the nature of existence, the definition of science, and the uniqueness of our universe. Another fundamental question in cosmology is the baryon asymmetry problem. Why does the observable universe contain significantly more matter than antimatter? According to the Big Bang theory, matter and antimatter should have been created in equal amounts, leading to mutual annihilation. Yet, a tiny imbalance, about 1 part in a billion, in favor of matter led to the residual matter that makes up galaxies, stars, and planets. In 1967, Soviet physicist Andrei Sakharov formulated 3 conditions necessary for baryogenesis, the process generating baryon asymmetry, baryon number violation, interactions that do not conserve baryon number, C-symmetry and CP symmetry violation, processes that differentiate between matter and antimatter, departure from thermal equilibrium, conditions that prevent processes from reversing symmetrically. Sakharov wrote, the very existence of the universe requires processes that violate the symmetry between particles and antiparticles. CP violation, where the combination of charge conjugation, C, and parity, P symmetries is not conserved, has been observed in certain particle decays, such as those involving kaons and B mesons. Various theories aim to explain baryogenesis. Electroweak baryogenesis proposes that baryon asymmetry arose during the electroweak phase transition in the early universe. Leptogenesis suggests an initial asymmetry in leptons, such as neutrinos, was converted into baryon asymmetry through Sphaleron processes in the Standard Model. The discovery of neutrino oscillations, indicating that neutrinos have mass, supports leptogenesis scenarios. However, the exact mechanisms behind baryon asymmetry remain unresolved, and current CP violation in the Standard Model is insufficient to account for the observed imbalance. Experiments like the Large Hadron Collider, LHC, Bell 2, and DUNE, Deep Underground Neutrino Experiment, aim to explore CP violation and the properties of neutrinos, seeking clues to this fundamental mystery. Exploring the universe, tools, discoveries, and profound questions. To probe the fundamental forces and particles that shaped the early universe, scientists utilize powerful particle accelerators. The Large Hadron Collider, LHC, the world's largest and most energetic particle collider, is at the forefront of this research. The LHC accelerates protons to 99.999999% the speed of light, colliding them at energies up to 13 tera-electron volts, TeV. These high-energy collisions recreate conditions similar to those fractions of a second after the Big Bang. In 2012, the LHC experiments ATLAS and CMS announced the discovery of the Higgs boson, confirming the last missing piece of the Standard Model and explaining how particles acquire mass. Physicist Peter Higgs remarked, "I am astounded at the amazing speed with which these results have emerged." Beyond the Higgs, the LHC searches for evidence of physics beyond the Standard Model, such as supersymmetry, extra dimensions, and dark matter candidates. Experiments like LHCb are dedicated to studying the differences between matter and antimatter by examining CP violation in B meson decays, contributing to our understanding of baryon asymmetry. Plans for more powerful accelerators aim to reach higher energies and greater precision, potentially uncovering new particles and forces that could shed light on dark matter and quantum gravity. Space-based telescopes have revolutionized our ability to observe the cosmos without atmospheric interference. The Hubble Space Telescope, launched in 1990, has been instrumental in measuring the universe's expansion rate and refining the Hubble constant. The James Webb Space Telescope, launched in December 2021, is the most powerful space telescope ever built. JWST's advanced instruments enable it to peer through dust clouds that obscure visible light, providing unprecedented clarity into star and planet formation processes. Ground-based telescopes equipped with adaptive optics and interferometry complement space telescopes by providing high-resolution imaging and spectroscopy. In 2019, the Event Horizon Telescope, a network of radio observatories around the world, captured the first direct image of a black hole's event horizon, confirming predictions of general relativity in extreme conditions. Upcoming missions will expand our observational capabilities. LISA will detect low-frequency gravitational waves from sources like merging supermassive black holes. Euclid will map the large-scale structure of the universe to investigate dark energy and cosmic acceleration. As NASA astrophysicist Paul Hertz stated, these missions will address fundamental questions about the structure and evolution of the universe. Advancements in technology and international cooperation continue to push the boundaries of exploration. These observational tools not only test theoretical models but also inspire new theories, driving the ongoing quest to comprehend the universe's deepest mysteries. As we stand on the precipice of knowledge, the universe continues to reveal its secrets while simultaneously posing new and deeper questions. The singularity at the heart of the Big Bang challenges our understanding of physics, urging us to develop a unified theory that can reconcile the very large with the very small. The concept of a multiverse expands our cosmic horizons, prompting us to consider the possibility that our universe is but one of countless others, each with its own laws and constants. The mystery of baryon asymmetry reminds us that even the very existence of matter is a delicate balance, the result of subtle processes in the universe's earliest moments. Through cutting-edge experiments and observations, from particle accelerators recreating the conditions of the early universe to telescopes peering across billions of light years, we continue to push the boundaries of what is known. The journey to understand the origins and fate of the universe is a testament to human curiosity and ingenuity. As we uncover new evidence and refine our theories, we move ever closer to answering some of the most profound questions about existence itself. In the final sections, we will explore the philosophical and theological implications of the Big Bang Theory, reflecting on how these scientific insights intersect with our deepest contemplations about the meaning and purpose of the cosmos. As we delve into the origins of the universe, we encounter profound philosophical and theological questions. The Big Bang Theory suggests that not only did the universe have a beginning, but time itself originated at this moment. This challenges our conventional understanding of causality, where every effect has a preceding cause. The concept that time began with the Big Bang implies that asking what came before the universe may be meaningless, as before necessitates time, a dimension that did not exist prior to the Big Bang. Physicists Stephen Hawking and Roger Penrose demonstrated through singularity theorems that under general relativity, space and time are linked and both emerge from the Big Bang singularity. This raises questions about the nature of time and whether the universe could be self-contained without the need for an external cause. These ideas echo the philosophical concept of causa sui, or self-causation, where the universe could be its own origin. Philosophers have long grappled with the notion of an initial cause or an uncaused cause. Aristotle introduced the idea of a prime mover, an initial cause that set everything in motion. Immanuel Kant argued that human reason is limited when dealing with concepts like the universe's origin, which may be beyond empirical understanding. Alternative models propose that the universe could be part of a larger multiverse or result from quantum fluctuations in a timeless state. These ideas challenge the traditional cause and effect framework and open discussions about the nature of reality and existence. The intersection of cosmology and theology invites reflections on creation narratives found in religious traditions. Many religions describe the universe's origin as an act of creation by a divine being. The Big Bang Theory, by suggesting a beginning, has been seen by some as compatible with these creation accounts, while others interpret it differently. While science seeks to understand the how of the universe's origin through empirical observation and theoretical models, theology often addresses the why, exploring purpose and meaning. The dialogue between science and religion continues to evolve, enriching our collective exploration of existence. Another philosophical consideration arising from cosmology is the fine-tuning argument. The fundamental constants of nature, such as the gravitational constant, the strength of electromagnetic interactions, and the cosmological constant, appear to be precisely set to allow the existence of a universe capable of supporting life. Even slight deviations in these constants could lead to a universe where stars, planets, and life as we know it could not exist. This apparent fine-tuning raises the question, why do the constants have the values that they do? There are several interpretations. Anthropic principle. We observe these values because only a universe with them could harbor observers like us. Multiverse theory. Our universe is one of many, each with different constants, and we happen to be in one where the conditions allow life. Intelligent design. Some propose that the universe's fine-tuning is the result of purposeful design by an intelligent cause. The anthropic principle comes in two forms. Weak anthropic principle. The observed values of all physical and cosmological quantities are not equally probable, but take on values restricted by the requirement that life can evolve. Strong anthropic principle. The universe must have properties that inevitably lead to the development of intelligent life. Critics argue that the anthropic principle is a tautology that doesn't provide a scientific explanation. Proponents suggest it offers a framework for understanding why the universe has the conditions we observe. Research into varying constants through simulations shows that most sets of values result in sterile or short-lived universes. This rarity fuels the discussion about whether our universe's life-permitting conditions are a fortunate coincidence or indicative of deeper underlying principles. Some scientists hope that a theory of everything might reveal that the values of fundamental constants are not arbitrary but determined by deeper laws. Until then, the fine-tuning argument remains a fascinating intersection of physics, philosophy, and theology. Our exploration of the Big Bang Theory has taken us on a journey from ancient cosmologies to the forefront of modern science. The Big Bang Theory stands as a monumental achievement, synthesizing evidence from astronomy, physics, and cosmology to describe the universe's origins and evolution. It explains the cosmic microwave background radiation, the abundance of light elements, and the large-scale structure of the cosmos. Yet the quest for knowledge is far from complete. Challenges like the singularity, the nature of dark matter and dark energy, and the unification of quantum mechanics with general relativity push the boundaries of science. Philosophical and theological questions about the meaning and purpose of the universe continue to inspire debate and reflection. As we look to the future, advancements in technology and collaboration among scientists worldwide promise to deepen our understanding. Projects like the James Webb Space Telescope, next-generation particle accelerators, and gravitational wave observatories will open new windows into the cosmos. Science is a collective endeavor, transcending borders and uniting us in the shared pursuit of truth. Each discovery brings us one step closer to answering fundamental questions about who we are, where we come from, and where we are heading. The story of the universe is, in many ways, our own story. A narrative that began 13.8 billion years ago with a cosmic event that set the stage for galaxies, stars, planets, and life. As we continue to explore the cosmos, we are reminded of the words often attributed to philosopher Socrates: "Wisdom begins in wonder." Let us carry that sense of wonder forward, embracing the mysteries of the universe with curiosity, humility, and a commitment to seeking understanding. Thank you for joining us on this voyage through time and space. The universe awaits us, vast, enigmatic, and filled with possibilities.